We've been doing these problems where these forces or loads are represented by arrows, or we've had beams, and there would be loads like this on them. Well, in real life, loads are not arrows. You don't have loads applied at a point, except maybe for knives. So knives are very sharp, and at the tip of a knife, when it's pressing down on something, that might be represented by an arrow. But in real life, loads are distributed. So here are some pictures. We have this set of boxes that are sitting on this rack, and this is just being distributed. That weight's being distributed over that pallet. Here we have snow, and this snow is being distributed over the roof, and even buses or cars on a bridge. You could think of these things as distributed loads over a bridge. And a famous incident of distributing loads was the Golden Gate Bridge. Here's normal traffic right here on the bridge. But on an anniversary of the bridge, they opened it up to pedestrians, and you were allowed to cross over it on foot. There was such a big crowd that by the time the first people got over to the edge, people were still coming on the start, and it was loaded like this. Well, people loaded like this here actually weigh more per square feet than regular traffic like that. And if you look at this picture of the bridge, it's flat, but normally it's arched like this. And it's the heaviest load that's ever been on the Golden Gate Bridge. It was more than it really should have held, and they're fortunate there wasn't a tragedy. But anyway, we want to know what to do when the loads are distributed like that and not just arrows that are saying 20 kips or 50 newtons or something like that. And here's the concept. When you have people standing on a bridge or cars distributed over a bridge, you get a load, P, that's per square foot. So that would be pounds per square foot, or newtons per square meter. That's how many pounds or newtons per unit area on the bridge. Well, the first thing we do is we multiply that pounds per square foot or newtons per square meter by the width. Then we have the width, let's say in feet, times P, which is in pounds per square foot. And we'll call that W, and the units come out to be pounds per foot. So this W here is in pounds per foot. So it's a certain amount of pounds for every foot you travel across the beam. Well, what we want to do for statics is to replace that pounds per foot into a total load that's in pounds or newtons, and we want to know where that load is located. We want the location of that, which we're going to call X bar. So again, the goal of this is to get the total force and the location X bar. Well, if you just think of this distributed load as an area, so here, this orange area here, the total load is just that area, the total area, and the location of that load is the centroid, or the center of gravity, or CG, of that area. To get the total load, again, it's the area under the load curve, and the area under a function involves integrating. Here we have W as a function of X, and if you want to get the area under that curve, you want to take the area of W dx, that's this little area that you're going to add up, and you can just express that as the integral of dA. dA is that area of this little strip, which is W dx, and the integral of dA is the area. So this proves that the force resultant equals the area. The centroid is the average x, and you know how to get averages. For example, you know how to calculate your grade point average. You take your grade times how many credits each class is and divide by the total credits. Well, think of grade as your x location and credits as your area. To get the average x location, you take your x of an area times its area, then add those all up and divide by the total area. Except we're not adding, well, we are adding because that's all integrating is. We're going to integrate. So we're going to do x times the area, or x dA, all over the total area, or integral dA. And this little integral here will give us x bar, which is the location of the resultant. This concept of getting the total load and its centroid will become clearer when we do some examples, but there are some you should remember. If you have a rectangle that has a base and a height, you should know that that area is base times height, and you know that the location of the centroid of a rectangle is just halfway over, b over 2. Well, if you have this triangle, base times height, you know that that area is 1/2 base times height, right? That's the area of a triangle. And you should also by now know that the location of the centroid is 2/3 of the base. Oh, let me write that in. The x bar for the rectangle is b over 2, and for this triangle is 2/3 b. Let me write that b over 2 is 1/2 b. Okay, so there we go, 1/2 b. Let's do one that you might not know. We'll do a parabola that right here the slope is 0, and it's also base times height. Well, that area, you can see it's smaller area than a triangle because it's got some parts missing. See, it's got this part missing. The area turns out to be 1/3 base times height, and its centroid actually moves over to where it's 3/4 b, and this is y equals kx squared. It's a parabola. Well, you can see a pattern happening. You can sort of guess what's going to happen if this is a cubic that's also tangent right there at the origin. If you have 1/2 kx cubed, and it has to do with taking the integral of x squared is 1/3 x cubed, integral of x cubed is 1/4 x to the 4th. But the area, if it's base times height, ends up being 1/4 base times height. See that? Think of this for the rectangle. That's 1 over 1. The area for triangles, 1 over 2. The parabola, 1 over 3. And the cubic, 1 over 4. There's a similar progression for the centroid. For the rectangle, 1 over 2. Triangle, 2 over 3. Parabola, 3 over 4. And not surprisingly, the centroid for this cubic is 4 over 5b. And again, both the parabola and the cubic only work if at the origin the slope is 0. Okay, here are some practice problems we'll do to get this concept. Just remember, we're looking for areas and centroids. This is a very typical problem. Most of the time, loads will be rectangular like this. Okay, so we have that load there, this load here of 3 kilonewtons per meter. Let me use a different color to contrast. And then this load here of 9 kilonewtons per meter over 3 meters. Okay, all we have to do is get areas and centroids. It's pretty easy. So 6 kilonewtons per meter. That rectangle has a height of 6 kilonewtons per meter and a base of 1.5 meters. The area of that rectangle is 9 kilonewtons. 6 times 1.5, and the centroid of a rectangle is halfway over, or 0.75 meters. Similarly, the area of the 9 kilonewtons times 3 meters, so 9 kilonewtons per meter times 3 meters is 27 kilonewtons, and its centroid is at half of 3, which is 1.5 meters from A. And finally, 3 times 1.5 is 4.5 kilonewtons, and its centroid is 0.75 meters from the end there. Okay, that was a pretty easy problem. Here's our second problem. It involves triangular loads this time, not rectangular. Again, all we're going to do is get areas and centroid. I'm going to break this into two triangles. So we have this triangle on the left here. I'm going to color orange. And we have this triangle on the right, which I'll color in green. Okay, you just have to remember the area of a triangle is 1/2 base times height, and its centroid is 2/3 of the length over, away from the pointy tip. So the area of a triangle, base 3, height 6, 1/2 base times height, that's 9 kilonewtons. And the centroid of a triangle is 2/3 of the base, which in this case is 2 meters, over from the pointy end. Here for the green triangle, 1/2 base times height, 1/2 6 times 6 is 18 kilonewtons. And again, 2/3 of the base is, in this case, 4 meters. And that's again from the pointy tip of the triangle. Notice that the units work out. The area, base times height. Height is kilonewtons per meter, and the base is in meters, so kilonewton per meter times meter is just kilonewtons. Here's our third problem, but unfortunately, we don't have a formula for the area or centroid of a trapezoid like this. So what we're going to do is break it up into a rectangle and a triangle. Let me color those in. Here's the rectangle we're going to look at, and here's the triangle we're going to look at. Okay, we can do this. The area of a triangle, 1/2 base times height. You take 1/2. Okay, the height is actually 3, right? The height of this triangle, because the green rectangle is 3, and if the total height's 6, the orange part's only 3. So we need to take 1/2, 3 times 4.5, and that comes out to be 6.75 kilonewtons. And it's at 1/3 from the tall side, or 2/3 from the pointy side of the triangle. I'll just do this. So 1/3 of 4.5 is 1.5 meters. Next we have the green green rectangle. So the area of a rectangle, base times height. This green rectangle, it goes over a distance of 6 meters total, and it has a height of 3 kilonewtons per meter. And then its area, base times height, is 18 kilonewtons, and it's at the middle of the total green rectangle, so it's at 3 meters from the left end. Let me show you another way to handle trapezoids. So let's say you broke it up into this rectangle and that trapezoid. Another way to do a trapezoid is to break the trapezoid into two triangles like this. Okay, let's do it this way. We have 3 pieces, but what I'm really trying to show is how to handle a trapezoid as 2 triangles instead of a rectangle and a triangle. Let me color in all the pieces. So we have this orange triangle there, this orange rectangle there, and this green triangle there. I'm not interested in that rectangle. You know how to do that. That's easy. So just 3 times 1.5 is 4.5, and of course halfway over, 0.75 meters. What I really want to do is to show how to handle this trapezoid. And this orange rectangle has a height of 6, and a length of 4.5. It doesn't matter that it's not a right triangle. The area of that is just 1/2 6 times 4.5. And that area is 13.5. And that's at 1/3 of the way over. So that's 13.5 newtons. And this distance is 1.5 meters, 1/3 of 4.5. The green rectangle is also 1/2 base times height. Its height is 3, the other height of the other side of the trapezoid. So 3 times 4.5 divided by 2. So we have 3, let me do this on my calculator. 3 times 4.5 divided by 2, 6.75 newtons. And it is at 1/3 of the way from here. And so that's 1.5 meters. I often like to break trapezoids into two triangles rather than a rectangle and a triangle, partly because I know this height is 6, that height's 3, and when you break it up into a triangle and a rectangle, to get the height of the triangle, you got to remember to subtract the height of the rectangle. Anyway, it's up to you how you do it. This last problem is a cubic, and it's tangent at A because the slope is the derivative of that, and when you plug 0 into the derivative, you get 0. We know this one. I went over it earlier. The area is just, let's see if I can remember, 1/4 base times height, which is base is 4, height's 160. And so that comes out to 160 newtons. And x bar is 4/5. 4/5 of 4, and that comes out to 3.2 meters. But I think how they really wanted you to do it is to do the integrals, so let's try that out. The area is the integral of w dx. And so that's just the integral from 0 to 4. That's where x is going. And w is 2.5 x cubed dx. And so that integral is 2.5 times 1/4 x to the 4th from 0 to 4. I'll plug that all in, and hopefully we get 160. And lo and behold, that does come out to 160 newtons. Okay, x bar is just integral x dA all over integral dA, and that will equal integral x dA, and we just did the integral dA, which is 160, and so that will equal the integral 0 to 4 x times 2.5 x cubed dx, that's dA, w dx is dA, all over 160. And so that integral comes out to be the integral 0 to 4, 2.5 x to the 4th dx, all over 160. And that's just 2.5 times 1/5 x to the 5th from 0 to 4, all over 160. And hopefully that comes out to 3.2 meters. And that integral comes out to 512 all over 160, and when you divide that out, drum roll, 3.2 meters, just like we got before.